Okay, so here we're going to take a look at reviewing, gosh, I don't even, all the way back to chapter 4, but basically the review is on the ideas of rates in and out, remembering your initial amounts, or just using the integral of f prime to find f values. So it can also come up just in the context of like graphs and maxes and mins and stuff. I'm going to start with the whole idea of rates in and out, and we've seen this tons and tons and tons of different ways. We've talked about gravel coming into a plant. There's been stuff about like sand. There's stuff about rainfall amounts. I mean, they can do any real life thing that they want. But just to review in general, let's talk about, let's say that A of t is our arrival rate of something. And we'll say that R of t is the removal rate or the processing rate. Or it could be the leaking rate. Because this could be arrival rate or filling rate. So I don't want to make a video that's specific to a question. I want it to work just in general. So if this is the case, and they ask you, let me scan through and see just a couple of different questions. Yeah, okay. So if they ask for the amount that arrives from t equals 2 to t equals 6, then I would take and I would integrate my arrival rate with respect to time from 2 to 6, because that question was only asking for the amount that arrives. But if they say, what is the total amount at time t equals 8, say. Well, then let's do a scenario, come back up and update our information. Say that we have an initial amount of 100, whatever, 100 ounces, 100 gallons per whatever. I mean, it just depends on what we're talking about. But we have an initial amount of 100. And say that, let's make this a more challenging example. Say that our arrival filling rate is good for t in the interval. Say stuff starts arriving from 0 up to like 24. We're doing like hours maybe. But that our removal rate is good for t, and that's good. It's getting too hard to read. Hold on. Let's do that underneath. Let's say this rate is good for t and not equals t in. Maybe 2 to 24, because maybe it doesn't make sense that it's going to be removed or processed until later. Maybe you don't turn on that equipment until you have enough to make it worthwhile to use. Or maybe in the case of a leak, the leak didn't spring until 2 hours into the day or whatever. And we can update that in this case t is in hours, but I didn't put units on anything else, so because again I'm trying to give you just a generic amount. So if they want the total amount at t equals 8, then I'm going to have to figure out, okay, so that total amount is going to be my initial that I already had, plus I need to figure out what arrives up until t equals 8. So that would be 0 to 8 of the a of t dt. That would be how much is arriving. Then I would subtract, and I don't want to subtract from 0 to 8 because, again, remember we talked about it wasn't being removed until 2. So I'm going to use 2 as my lower bound, which means I can't put these in the same integral. And that was called, sorry, did we call it R for removal? Yeah. A lot of the questions you see, it will be removed the whole time. And so then you could do, in that case, an integral from 0 to 8 of a of t minus r of t, all of it like that, dt. But we can't do that here because it wasn't removed beginning back at 0. It was only removed beginning at 2. Okay. The other thing that they might ask you, so the difference between the amount that arrives versus the total amount that you have, then they might want to know a time with a maximum amount. So in that case, if you want to maximize something, then you need to think about that thing that you're maximizing. You need to give it a name. And I would say A for amount, but I kind of can't because A is my arrival rate. So let's say T is equal to the total amount at time little t. So I have a function big T of t. That's going to have to equal the 100 that I have plus the integral from 0 to little t, and now I can't write a of t anymore because I can't repeat that lettering. So I'm going to switch it and do a of x dx, and I know that the t is going to get plugged in once I integrate. Minus, and again it was only getting processed from 2 up, so 2 to little t of r of x dx. You can always switch out the lettering on your function if you need to, and I need to here because this bound is going to get plugged in for t's. I don't want there to already be t's there. So that would be my total amount. Then I would want to take t prime of little t. And in that case, when I take the prime, the 100 is going to go to 0. And then this becomes a second fundamental theorem case where the integrals and the derivative are going to wipe out. So this is going to become a of t minus r of t. So really, to find my critical numbers, I want that when t prime is equal to 0. That means when a is equal to r. And I want when t prime does not exist, and most of the time that doesn't happen, but you'd have to look through your scenario and see if there were any denominators. Then, if you have bounds, you would go and check them in the original. So if you have bounds, then you would check t of the first bound, you would check t of any critical numbers, and you would check t of the last bound. And the highest value would be your maximum amount, and the lowest value would be your minimum amount. So that's just in general if you're working with word problems. The other way you could use this is looking at integrating f prime to find f values. So if I had to integrate f prime to find f values, that would be like maybe you are given a graph of f prime, and you maybe say you want Max's max min values. So that would be actual F values. Okay, well, say you established that you need to check, I don't know, x equals 3 and -1 and 1/2, or something like that. So those are the ones I need to check. Say that you know you have to know one value to start with. So say you do know one of them. Say they came out and told you what f of 3 was for some reason. Well, okay, so then if I already know that, then if I need to check f of 3, I could just put what it is because it was given. But if I need to check f of -1, then that's going to equal my initial amount, which I know about, f of 3, plus the integral from what I know about, the 3, to what I want to know about, the -1 of f prime of x or t or whatever it is. Okay. And then if I was given a graph, this would be going backwards on a graph. So if it's from a graph, then I would have to say this is really equal to f of 3 minus and integrate from -1 to 3 f prime of x dx. And for this from the graph, do area accumulations. Okay. If it's not from a graph, it doesn't matter that those bounds are out of order because when you do your subtraction, it'll take care of itself. And you would do the same thing for the f of 1/2. But basically what this is pointing out to you is that if you want, so you would have the function value that you want is equal to the function value that you know plus, and then you integrate from the time that you know to the time that you want of the derivative. It's really, really important that even if it makes it out of order, you put what you know for this value here and for the bottom part of your integral. Okay. That's all coming back. It's really coming from the first fundamental theorem of calculus. Oops, sorry. Not the second, where you differentiate outside, the first. And that would say if I integrate little f prime of x dx from a to b, I get little f of x from a to b, and that's the same thing as f of b minus f of a. And then just rearranging to figure out what I want. So it would be saying, okay, I'm going to add f of a to this side and then have the integral from a to b of f prime of x dx, and that's equal to f of b. And that's what we summarized up here. The order has been flip-flopped as far as what's on which side of the equal sign. That's what we summarized here. While we're at it, since we're reviewing, it might not be a bad idea to review, okay, how is that, oops, sorry. How is that similar to second fundamental theorem of calculus? That talks about if the derivative's on the outside. This is if the derivative's on the inside. So second fundamental theorem is d dx of, and if you had an x like up here, and then maybe let's make a complicated one. Maybe you had x squared down here, and this is f of t dt. Notice in this top example, I had a derivative that was on the inside of my integral. Notice in this example, my derivative part is on the outside. Okay, if it's on the outside, this wipes out. This becomes f of x times chain rule on the x, which is 1, minus f of x squared times chain rule on the x squared, which is 2x. I do not do chain rule on the actual function itself, and that also means if I have bounds that are constants, when I do chain rule on them, they go to 0, so that would go away. But I do think it's worth kind of comparing, because once we did all of that in Calc AB, then I would have students, and I've even seen it in here, where we would integrate f of t dt from a to b, and I would have students telling me that's f of b minus f of a, and it's not. That's completely false, because you had the same f here, here, and here. You didn't do anything with it. The only way that I'm going to get that f back out is if I'm differentiating on the outside so it wipes out, or if I had f prime inside, so when I integrate f prime, I get f. Okay? But just in general with these word problems, you could memorize this piece that we talked about up here. So if you just knew this information, you would be okay. If it's easier for you to go back to the fundamental theorems of calculus each time and write out your equation and do the math and move stuff over, then you're welcome to do that, but you don't have to. The tricky part is just making sure that the value you know here is the start of your integral, even if that means with a graph that I have to change my bounds around. Because from a graph perspective to integrate, I need to go from left to right. Okay? This should be all you need to do the packet reviewing initial values, because we've covered what it looks like from a graph and we've covered what it looks like from word problems.